You know, we spend our entire lives walking around on the surface of our planet, but have you ever really stopped to think about what's going on thousands of kilometers right under your feet? It is a hidden world with crushing pressures and temperatures as hot as the sun. So let's take a journey there. But that brings up a really big question, right? How in the world do we know what's down there? It's a huge problem. I mean, we can't just dig a hole and go take a look. The conditions are just way too extreme. So, how did scientists figure out the internal map of our planet without ever actually seeing it? To really get a sense of just how big this challenge is, check out this number: 12,262 meters. That is the depth of the Kola super deep borehole in Russia. It's the deepest hole humanity has ever managed to drill. And it was an incredible feat of engineering that took decades. But get this, that 12-kilometer hole, as deep as it sounds, it barely scratched the surface. It didn't even make it all the way through the crust, which is the thinnest layer of the planet. If Earth were an apple, we basically just managed to pierce the skin. That's it. Okay, so if we can't drill our way to the center of the Earth, how have we solved this planetary mystery? Well, scientists have had to become detectives, piecing together all these indirect clues and searching for the planet's hidden fingerprints. The first huge clue actually comes from the planet itself. Whenever an earthquake happens, it sends out these incredibly powerful energy waves. We call them seismic waves, and they ripple right through the Earth's interior. You can think of these waves like a planetary ultrasound. As they travel through different materials, from solid rock to molten metal, they bend, they change speed, or sometimes they just get blocked completely. By tracking where these waves don't show up on the other side of the planet, scientists can map out what they call shadow zones. And it was these shadows that gave us the first solid proof that Earth's outer core has to be liquid. Now, the next clue, it doesn't come from inside the Earth at all. It actually comes from outer space. Meteorites. They're these ancient leftovers from when our solar system was born, about 4.5 billion years ago. They're like little cosmic time capsules. A lot of these meteorites are made of dense iron and nickel. And since Earth was formed from that same original cloud of gas and dust, scientists figure that these metallic meteorites are basically a sample of our planet's starter kit. The very same stuff that sank down to form the core. It is the closest thing we'll ever get to actually holding a piece of the Earth's core in our hands. So, when you put these clues together, they paint a really clear picture of a planet with very distinct layers. So let's do it. Let's take a journey from the surface we all know right down to the mysterious center. We're going to start with the crust, that thin, brittle shell we all live on. And what's interesting is there are actually two different types. You've got the continental crust, which makes up the land. It's thicker, less dense, and mostly made of granite. But then there's the oceanic crust, under the seas, which is thinner, much denser, and made of a dark volcanic rock called basalt. Okay, go a little deeper, and you hit the mantle. This is the thickest layer by a long shot. It makes up most of our planet's mass. It's this hot, dense layer of rock, but it's not totally solid. Over millions and millions of years, it actually flows, incredibly slowly, kind of like a giant river of super thick tar. And at last, we get to the very center, the core. And it's split into two completely different parts. You have a churning liquid outer core made of molten iron and nickel, and then a solid inner core made of the exact same super hot metals. Now, wait a second. That seems like a total paradox, right? How can the hottest part of the planet be solid? Well, the answer is one word: pressure. The weight of the entire planet is pushing down on that inner core, creating pressure that's more than 3 million times what we feel up here on the surface. That pressure is so intense that it forces the iron and nickel atoms to lock together into a solid crystal, even when it's hotter than the surface of the sun. It's just incredible. Okay, so we've got all these layers. Who cares, right? Why does any of this matter to us up here? Well, because these layers are anything but static. They form a powerful dynamic engine deep inside the Earth that shapes our entire world. This whole engine is driven by a process called convection, and it happens in both the mantle and that liquid outer core. It works just like a boiling pot of soup on the stove. The hot stuff at the bottom gets less dense and rises up, then it cools off near the top, gets denser, and sinks back down. This creates this slow but unbelievably powerful circular current. And this internal engine has two massive impacts that honestly make life on Earth possible. In the mantle, that convection is what drives the slow drift of the continents. And in the core, it's what generates our planet's protective magnetic field. I want you to imagine the Earth's crust not as a solid shell, but more like a cracked eggshell that's broken into these massive pieces we call tectonic plates. These plates are just floating on top of that slowly turning mantle below, and the convection currents in the mantle are constantly dragging them around, causing them to smash into each other and pull apart. That is plate tectonics, the engine behind earthquakes, mountain ranges, and volcanoes. At the same time, deeper inside the planet, something even more important is happening. As all that liquid iron in the outer core churns and swirls around, the movement of that molten metal acts like a giant dynamo, generating a powerful magnetic field that wraps around our entire planet. And this magnetic shield is absolutely vital for life. I mean, it deflects this constant, dangerous stream of charged particles from the sun, which we call the solar wind. Without this shield, that solar wind would literally strip our atmosphere away, leaving the surface barren and totally irradiated. It's also the reason a simple compass points north, and it's what creates those stunning auroras at the poles. So, the really crucial thing to understand is that our planet has been this dynamic, evolving system right from the very beginning. It started as a molten ball of rock, but over time, the heavier stuff sank to the center, the layers formed, and this amazing internal engine kicked into gear, creating the stable, protected world where life could actually take hold and flourish. But that internal engine is powered by heat, and it's slowly losing that heat. The core is cooling, even today. And that leaves us with a final, pretty profound question about the very distant future of our world. What happens when that engine eventually cools down and stops running? What happens when our protective magnetic field fades away? It's a powerful thought to end on, a reminder that the solid ground beneath our feet is just one part of an epic, ever-changing cosmic story.